Okay. So just I won't repeat what I said. Hopefully there'll be a way to add it to this recording. But coming to quantum Hall effect, so what I was saying is whenever there is a complete change of paradigm, when you are not just building on existing principles, the wave function becomes a very important way of attacking the problem, because it allows you to build in intuition without fully justifying it. It's a variational state. You don't know whether it is the true ground state, but you know that the energy will be bounded. The ground state energy will be bounded, uh, or in other words, I should say that the variational energy will be an upper bound to the ground state energy. Similarly, moving on to high temperature superconductivity, again, nobody had seen such a phenomena ever before. And once again, Anderson proposed a very different kind of wave function from even the BCS wave function. So whenever there's a change of paradigm, you see, so superconductivity was understood to happen when you have attractive interactions. Now you had in high temperature superconductivity, the interactions are actually repulsive. So you wouldn't even think of getting a superconductor there. But rather interestingly, through the route of magnetism, exactly the kind of magnetism we are talking about, it was possible to make singlets between two electrons, and these singlets became the prototypical Cooper pairs, which then went on to Bose condense and become the ground state for the high TC superconductors. It's called the resonating valence bond wave function. So I've put down 4 really powerful examples where wave functions have been instrumental in solving a many-body problem. But now I want to move to methods that we can kind of lay down a programmatic way of attacking a problem. You can say, okay, start with this, then do this. This is how the interactions are put in, and that's how you solve it. And this is where the path integral methods that we just started discussing, where it's a quantum problem in d dimension space. We add another dimension of time, and we look at how spins evolve in time. This is imaginary time. Or they could be bosons or fermions. How do they evolve in time? And the statistics shows up in how these paths exchange in imaginary time. I will tell you more about that. So that is how now we can set up this path integral, formally at least, and we can do some small delta tau approximation, and now we have an action that in principle, at least we can evaluate. It is still very hard to evaluate it, so that is where often the path integrals are evaluated numerically. The other method, if you can look at perturbatively the problem at low coupling and high coupling, then you can set up Feynman diagrams, sort of like what we did for the 5-4 theory. And the third method that I've put here is what I call an effective field theory. So let's say you start out with your underlying degrees of freedom, which are electrons. So let me give an example, like electrons in one dimension. And in one dimension, electrons interact very strongly, right? Because it's literally a single wire, 2 electrons move and they will have, they have to interact strongly. There's no avoiding, like there's no social distancing in 1D. You're bound to, either you don't move at all, but if you're in a band state and you in some momentum state, then you're bound to encounter another electron in one dimension. So in such a situation, you can often write an effective theory based on some emergent degrees of freedom. And there are different ideas here. I'm not going to go through this in this course, but in a way, this picture here gives you an idea about where you can go beyond the course. So for example, effective field theories are very important in condensed matter because we try to write down a simpler emergent theory that we can then handle perturbatively or by other methods. So under this, I have put down bosonization, conformal field theory near critical points, Chern-Simons theory for quantum Hall, and so on. Okay, so that was kind of a longish introduction, but I wanted you to have this kind of big picture in mind, because very often we kind of delve into a model and we go on it for a long time, but it's good to keep this big picture. Let me just stop here very briefly and see if you guys have some questions here.
So I have a question.
Yeah, Yanjun.
Yeah. So can you tell me why people believe that REB is the ground state for like high TC superconductor? Because I know that there's no numerically support for that, but people are just saying that, well, REB is the ground state of that. So I just don't understand why people believe that.
Okay, this is a topic which is very, very close to my heart. I worked on this for several decades, and at a time when no one believed it, and turned people's ideas around, including Anderson, who had, by the time, we came around with some of our work, Anderson himself had given up on RVB and was thinking about interlayer pairing. And there's a very interesting story. I met him at one of the conferences and I told him about some of our work. And he said he has inscribed in one of the More is Different books for me, saying, thank you for bringing me back to my own theory. I was right before I was wrong, in his own inimitable style. But let's leave this for another day, and I can tell you about the beauty of this wave function. So
Okay.
one of the important things here is when you write a Hamiltonian, right, in condensed matter, that Hamiltonian is already an approximation.
Mm-hmm.
So we really don't know what is the correct Hamiltonian for cuprates. Also, even when you write down a Hamiltonian, let's say a Hubbard model, whether the variational wave function is the exact wave function is also hard to determine. So
Yes.
the way one approaches such problems is by making predictions that can be experimentally verifiable. Okay,
Mm-hmm.
so that is what you can do. So for example, with RVB wave functions, you can make predictions for the spectral function, for the quasi-particle weight, all of these things that we haven't discussed in this class, but you can make predictions for angle resolved photo emission spectroscopy, and these have been verified. So that is what gives some credibility to such wave functions. Whether it is exactly this is difficult to verify, but it's something like this.
Okay.
Okay, great. Any other question? No. Okay. Let me turn to now this kind of a mapping. So pretty much in this course, I will be doing spins and bosons. I will not be able to get to fermions. Okay, so that's kind of where this course will end in the next 6 more lectures. So, okay, let's start with a familiar model. So we have been looking at spin-spin interactions. And let's take here today the O3 model. So we have done so far Z2 and O2, the XY model and the Ising model, which is Z2, and O2, which is the XY model. And you can combine all three components and write a O3 model. That's called the Heisenberg model. So I have a Hamiltonian, which now S dot S, these vectors, you can expand it into the X, Y, and Z components. And the X and Y components can be written with this factor of half as S plus S minus plus S minus S plus. So spin raising and lowering operators. And the ZZ Ising interaction. Okay, so far so good. Next, what I'm going to do, so I'm taking spin half models. So you can do an exact mapping of the spin operators to bosonic operators. And let's see how that goes. So the spin raising operator at a site becomes the boson creation operators. So you must have done harmonic oscillators. Think of those kinds of operators. I'll tell you where the difference comes in, but these are exactly like your harmonic oscillator operators. Creation and the spin lowering is a boson destruction operator. And you can write the SZ operator just as S plus, S minus, minus half, which is essentially N minus half. So you can see if this acts on a state where there is a boson present, N will give you an eigenvalue 1. 1 minus half is half, and that's SZ. So basically, spin up maps to there being a boson, spin down maps to an empty site. Okay? Now, the difference from harmonic oscillator operators comes in because these are spin half operators and they map to hardcore bosons. So these spin operators commute on two different sites, but on the same site, they anti-commute. So if you apply B, and that translates into when you apply B dagger twice at a site, you get 0. Okay, so that is what is different from usual bosons. These are hardcore bosons.
So I have a quick question about this.
Yeah.
So since B dagger square equals to 0, why can we say that it's a fermion instead of a boson?
Yeah, so these objects are peculiar on two different sites. They have bosonic commutation relations. On the same site, they have fermionic commutation relations. Okay, so that's what your Pauli matrices are. So
Okay.
we should, that's why we call them hardcore bosons, because
So in last class, we just solved this by introducing a string operator. Is it not possible to do this on this one?
Yeah, so in 1D, you can do it. The problem with these string operators in 2D becomes very complicated. So it doesn't remain, these representations are exact. So you can do them in any D, but they don't remain useful in higher dimensions. So what I'm setting up is now going to be general for any dimension.
Yep. So I have a question.
Yes, go ahead.
Yeah. So generally, when we talk about the spin models, we have the Holstein-Primakov transformation, which we do for spin wave theory. Is there any relation? Is there any relation between the two?
Yeah. So in general, if you have spin S, right? I'm talking about here spin half. So each site just has two states, either up or down spin, or in boson language, occupied or unoccupied, right? But in general, if you have a spin S operator, you will have 2S plus 1 states. That can be mapped to bosons with some cutoff. Bosons can have, in general, any number of bosons at a site, but this will, a spin S problem will translate to a 2S plus 1 possible bosonic states, or you can think of colors, So if you take that transformation, which I won't talk about here, but if you take that and write it for spin half, it translates to exactly this hardcore boson.
Okay.
Yeah. So another important point to make here, in general, coming to Yanjun's question, you can transform spin operators into fermionic operators as well. All of these transformations are allowed. These are operator transformations. They are all possible. It just depends on what physics you are looking for. Okay, so let me give you some insight here, because you will see in the literature, people take spin problems and they write it as bosons, sometimes as fermions, sometimes as Majorana modes, so all sorts of things happen. So the way you pick what kind of transformation to choose depends on actually the answer you're looking for. Because we don't solve the problem exactly, right? So we have some intuition, what are we solving for? So let's say your spin Hamiltonian is going to give you an ordered state. There's going to be long range order, okay? Then you would pick a bosonic representation. Because bosons, I will show you today, will develop what is called long range order, and that will be the sign of superfluidity in the bosonic system. And that will equivalently indicate that your spin problem has long range magnetic order. Okay, so if you are expecting to get order, that is the transformation you use, because ultimately you don't solve the problem exactly. You will make judicious approximations around some ordered state to see how the fluctuations reduce your magnetization. On the other hand, if you are studying, let's say, a problem where you think you should get a spin liquid, so in a number of problems that I do with quantum spin liquids, you try to make fermionic representations, because fermions don't have long range order. They give you Fermi surfaces or some other kinds of surfaces that touch at Fermi points. So if you're expecting no order, you make fermionic operator representations. Okay, so that's getting a little ahead, but right now, let's say we are looking at the Heisenberg model, and we want to kind of understand what is the long range nature of the long range order, what is the magnetization, if it's ferromagnetic, and if it's antiferromagnetic, what is the sublattice magnetization? That's the question. And of course, we can solve the spin problem, but I want to bring in the boson problem just to introduce the language and for you to see two equivalent ideas flowing through the two representations. Okay, so now we have our mapping. Last time I was told my screen froze when I did the recording. Are you able to see my screen moving? Okay.
Yeah, I'm able to.
Okay, great. So here is the spin Hamiltonian, and I've now written it as a boson Hamiltonian. And you can see that it has, in the boson language, what it is describing is, I've put it in this table. So let's say HXY acts on a state which has an up and a down spin on two sides. The XY component will basically flip these spins, right? So if I had an up down, it'll make it down up. That's what the XY Hamiltonian part will do. In the boson language, this initial state would have meant I have an occupied state at 1 and an empty state at 2. The XY Hamiltonian will basically interchange the empty and occupied sites, which is amounting to the boson at site 1 hopping to boson at site 2. Okay, so spin flips are becoming boson hopping terms. And the Z term just leaves it unchanged, and you get some basically prefactor coming from the SZs acting on those states. Or in terms of the bosons, it comes from the density-density interaction on the two sites. So let's say on site 1, there is a particle, so that gives you 1 minus half. On site 2, there was no particle, so you get 0 minus half. And that's how you get the prefactor for that Hamiltonian.
I have a doubt. May I ask?
Go ahead, Sandeep.
Yeah. So when you call it hardcore boson, you assume that you can't have like more than one occupation at a site. So is that's correct?
That's right.
So there's an energy cost for like infinite. You can say an infinite energy cost for like putting like more than one bosons at the same position.
Exactly. So in other words, you could have put a term here plus U Ni square,
and U goes to infinity.
And U goes to infinity.
Okay, so yeah, so this match, yeah, this dictionary where you map from spin to boson only work in that limit. Is that?
Yes, yes.
Okay.
So another way to think about it is you have your full Hilbert space for bosons, with arbitrary occupancy at a site, and you project from that full Hilbert space just these states. So
Okay.
you can make it even more formal by putting projection operators.
Okay.
And that's another very useful way for doing these kinds of problems, where you apply, it's a bit like the projection operators are a bit like what I introduced in the transverse fieldizing model. We had a whole slew of states. Let's say everything was pointing to the right, then you had one to the left, and like that you created a whole tower of states, and then you can start projecting from that set of states.
So I see that there's this operator level like dictionary between the spins and boson, but at the wave function level, you have an anti-symmetry in the spin language, but you have a symmetric wave function in the boson. So would that be a problem, or
no, because the way you can do is so you can write every operator, or let me see, oh, this is on another machine. Okay, so you can define a projected operator as a P operator, P dagger, right?
Mm-hmm.
That's a projected operator, but you can also have these projection operators act on the wave functions. Okay. So you can project on the Hilbert space of the wave functions and then operate the unprojected operator on projected wave functions.
I'm sorry, can you, so you're saying if you project the wave function of boson to like just one particle, they will have some anti-symmetry? Is that what you're trying to say?
Yes.
Okay.
Yeah.
I mean, these are bosons, right? So
these are bosons, and in a way, the B dagger square equal to 1 is the fermionic aspect of. So the key point here, it's not anti-symmetry. I should point out this very important difference. It's not anti-symmetry, but zeros in the wave function. Let me actually switch to my tablet and see if I can explain this, because this is kind of important. Let's see. I come here and I say share screen. Yeah. Do you see another screen coming on?
Yep.
Okay. Let me just see if I can add a bit of space here. And okay. Can you see my pen writing something? I've just drawn two axes. Yes. Okay. Yep. So what I'm trying to draw here, let's take a many body wave function psi, which depends on R1 through Rn, right? These are the coordinates of the particles. They could be bosons, fermions, or whatever. Now, how would this wave function look like as a function of one of the coordinates? Let me pick one of them, say R bar. And I fix everything else and I just change R bar. So basically, if you have a bosonic wave function in the ground state, you don't want to put any nodes in the many body wave function. It will look like this. It's always positive. It can be 0 if there is a hard core, but it will not change sign. So that's a bosonic wave function. If it's a fermionic wave function, because of anti-symmetry, you will, you exchange two bosons, two fermions, and you can get a sign change. So that's the difference. Okay. Is everybody with me?
I'm sorry, the in for spins, the anti-symmetry comes from the spin part of the wave function. Is, I mean, how
So you could even have spinless. Suppose
okay.
they are spinless fermions. Right now I'm just discussing spinless fermions.
Okay.
You exchange two spinless
Okay.
fermions, you should get a sign change, right?
Yeah.
And what I'm saying is, in the case of bosons, your wave function will always be positive. It can be zero if you have hardcore constraint. Like for helium, you would get a zero if you have two helium particles on top of each other, right? So what am I doing? What is this picture telling? That I fix all my other coordinates except R bar. So let's say R bar is one of the coordinates. And I move R bar. So let's say R bar is equal to one of the bosons sitting at some point. The wave function there will go to zero because there's a hardcore constraint. Okay?
Okay.
That's what I'm saying. Now spins, the Pauli matrices are interesting operators. They share both commutation relations of a set of bosonic kind, but on site, they have anti-commutation relations. So that's why this dual character comes in. But we can still regard them as bosonic with hardcore constraints, the way that it will still not give you the sign change as I'm talking about for fermions. Okay.
Okay.
And we can discuss this more. Let me go on. Let me stop sharing here and go back here. Okay.
I have a question.
Yes, go
Quick
ahead.
question. If JXY is different than JZ, do we still have O3 symmetry?
No, you don't have a O3 symmetry, but you can continue with the mapping.
Okay.
Okay. So I started out with the Heisenberg model as a motivator for a spin model, which arises in many magnetic systems. But actually, at this point now, if you start with the Heisenberg, Jxy is essentially J over 2 and Jz is J. But you can now make them just independent parameters and enrich this model all the way from studying an Ising model when Jxy is 0 to, by the way, is my screen being shared now with the mouse rotating around?
Yes.
Okay, so now you can just look at, that's why this model is so nice. It interpolates between the Ising model, the XY model, which we have been doing also, that had the vortices in 2D and all that. And you can take any intermediate value in between. In terms of bosons, what this means is that you have, sorry, I should have written JXY here. You have a Hamiltonian that describes hopping of bosons on a lattice. So that's like saying, okay, I have some kind of a, a kinetic energy of bosons on a lattice. Now it looks deceptive. It looks like it's a quadratic Hamiltonian, but we have to always remember that there's a constraint in the commutation relations that these are hardcores. Or as Sandeep was saying, we can put a U term and make U large. And so that's why even just the hopping term is not a quadratic term. It has strong interactions in it. Okay, so this is your minimal model, the JXY part, to study Bose-Einstein condensation. I shouldn't say minimal model. This model is a strongly interacting model for bosons that will show Bose-Einstein condensation. Then the second term talks about bosons having inter-site interactions. And this will lead to some kind of localized phases. So there's a competition here between a term which wants the bosons to remain a certain distance apart and minimize the energy, and this other term which wants bosons to hop, and it scrambles up that nice localized pattern. Okay, good. So you're getting the two languages, right? Given how much I'm talking. Okay, now let me come to another pictorial way of just writing the path integrals. So you see here, when we did the transverse fieldizing model, we had X dimension space, we had a D-dimensional space, and I'm just showing some variable here, X, that's space, and we had time, tau. And I'm looking at one site, and as you move in time, the spin can kind of flip because of the HX term, right? So the spin can flip and it can have some history. That history in terms of bosons is shown here in this green one. So you have a boson at a site, at a later time, the boson is still there. Then the spin has flipped. So that means my boson is not there anymore. Where did it go? It tunneled to a neighboring site. And then at a later time, the spin flipped back, and that shows up as the tunneled boson returning to the original site, and so on. So this trajectory, which can tunnel and deviate from a straight line, the moment a boson path deviates from a straight line, it's an indicator of boson tunneling. Okay, so that's how the boson path is getting constructed. Now, quantum fluctuations, which is the main topic of how phase transitions are driven. In the Z basis, we talked about spin flip processes caused by the HX term as introducing quantum fluctuations. Now in the boson language, you see that in some configuration NZ, the density, which is fixed at every site, any of these tunneling events will be the way to think about quantum fluctuations in the boson problem. Good? So you're getting this picture? Okay. So now let me quickly come to actually, I might just skip the ferromagnet. Or let's do that quickly, because the ferromagnet is easily solved exactly either in the spin or the boson language. But let's do it quickly. And then the more interesting result is for the antiferromagnet. So, you all can guess that if your Hamiltonian is minus j s dot s, the ground state has O3 symmetry in the high temperature phase, and it will break that symmetry in the low temperature phase by picking a particular direction and ordering along that. So let's say it picks this Z direction and every spin lines up. This state is the ground state you can show for the Heisenberg model. And you can show that very easily because when your HXY acts on this state, it is 0, because HXY wants to flip spins on neighboring. It'll flip one, it has a S plus, S minus kind of term, right? So it cannot do that. There are no down spins to flip up in this ground state. So the HXY is not able to introduce any fluctuations, right? And you can see this in the boson description. All the spins up is equivalent to there being a boson everywhere. Well, these are hardcore bosons, so clearly nothing can hop. So once again, HXY doesn't mix anything into this state, and this remains the exact ground state. Okay, great. Let's look at the antiferromagnet. A completely different situation happens here. So let's write it as the Z term plus the XY term. And you can see that the Néel state, which is this alternating up and down spins, again, your ground state has O3 symmetry and it picks this particular state, let's say. So in this case, okay, it's the Ising model. So it had Z2 symmetry and it picks one of them. And you get this particular ordering. It could also have picked down, up, and that's the other symmetric, Z2 symmetric partner. So now if you look at this state, you can see, okay, it has some Néel energy. which is proportional to, or rather it is this number, say in a square lattice, this would have been j over 2. I think my notation is that z counts the two independent neighbors. Okay, so this is the Néel state energy. But you can see right away, this is not the ground state. Because if you look at hxy, then hxy can flip two spins. So if it flips, if you start with up, down, it'll flip, let's say, this bond down, up. One of the terms will flip that. Another term may flip 3 and 4, and so on. So you'll have a whole host of these configurations with flipped spins mixing with the ground state. And sorry, not ground state, mixing with the Néel state. And so the end result is that the Néel state is not an eigenstate of H. So what is the eigenstate? Okay, so we'll come to that. But before that, let me just make sure everybody understands what is going on. So another way to think about this state, the up, down in the boson language is you have a boson, empty site. Boson, empty site. You know, they are again trying to remain as far apart as possible. You have n sites and n over 2 bosons, and they are remaining as far apart as possible. So that's the Néel state. What hxy does is it forces spins to, forces these bosons to hop to neighboring sites. Now you may think this is really bad for the bosons to do this, but we will come to that discussion. For now, at least you can see that the hopping is what is mixing other configurations into the Néel state. Questions?
So in the ferromagnetic case, when you were saying that all the spins pointing in the same direction is the ground state, so I understand why it's the ground state of just Hz, but how can we also say that it's the ground state of the entire thing just because the
because it also
other term would give 0?
Yeah, because it also minimizes the full Hamiltonian. Right, because the matrix elements for the second term, hxy, is 0. So the...
Couldn't it also be negative to make the energy even lower?
No, not possible. Okay, so that you should think about that question. So think about Brad's question, could you get negative terms? Okay, and this is where the boson language is very easy to see. Okay, I won't dwell on that right now, but that's a good question. Think about it.
Hi, is there any constraint on the number density of bosons? Like for fermions, we have the chemical potential which sets the number density of fermions. So do we have like, should we put in a term which is like minus mu b dagger b sum over all sites?
Yeah, so that's right. We can put in that term, but here in this mapping, yeah, we can. So in the spin problem, we have n sites and n spins, right? In the transverse, let's think about the spin first. In the transverse field Ising model, SZ was not a good quantum number, total SZ. Right? Here we could look at the problem SZ total by sector. We could do that. So let me bring up the following. Like in the ferromagnetic problem, right? The way I wrote the state, I basically had n sites and n bosons.
Yep.
But when I came to the antiferromagnet, I am looking at I'm going to, in the antiferromagnet, I have, where is that problem? Sorry, here. In the antiferromagnet, I have this state, up, down, up, down. So I have moved into a different SZ total sector. I have moved into SZ total equal to 0 sector.
Yeah.
Okay. And that means in the boson language, I have n sites, but n over 2 bosons.
Yeah.
So we could discuss a ferromagnet in any sector. So suppose I had fixed the sector to be SZ total equal to 0, right? How would I think of a ferromagnet in that sector?
You can have all n by 2 up spins, then a domain wall, then n by 2 down spins.
Yeah. Or in this kind of a quantum problem, it would be a kind of a cat state, or it could be a triplet. It would be a soup of triplets. So you take 2 sites and you make up, down, plus down, up. That's a triplet. And then you make a linear superposition of these triplets, and that would be the ferromagnet, an entangled ferromagnet.
Okay.
If you put the constraint of using SZ total to be 0. Did everyone see that? Like, let's say I have 2 spins. And I say, what, suppose I'm looking at a ferromagnetic problem with 2 spins. Then the ground state is going to be all up or all down. But if I force the sector to be SZ total equal to 0, then it'll pick up the up, down, plus down, up as my state for these 2 spins. Okay. Okay. So now
Sorry, can I ask a question?
Yes.
I don't really understand what you mean force SC total to be 0. Like, why would we be doing that?
So the reason is, you see, this comes back to how we control. So let's think of the particle representation, right? When you think of particle representation, I can't simultaneously write on the same platform. Okay, when you think of the particle representation, you can have a chemical potential which controls how many particles you have. That's what Nishchal was also bringing up, right? Okay, let me see if I'll switch to my tablet. Maybe that's the better platform. My tablet doesn't always work well, but let's see if I can. Okay. So are you able to see my second screen, which I'm moving now?
Yes.
Okay. Let me jump all the way to, or actually, I don't even know where that is. Okay. Let me try to do it here by adding some space. Okay. So what I'm saying is, think of the boson problem, right? What do we have? We have a lattice. I'm just showing it in 1D. And on this lattice, so I have some sites, n sites. But in general, I can have NB bosons, which doesn't have anything to do with how many sites I have, right?
Right.
So, and now the next thing is, so I'm trying to construct the Hamiltonian for bosons. And now what can these bosons do? These bosons can hop from one site to another. And okay, so they can hop. So that's some matrix element T. We often write minus T because you gain energy. You lower the energy by hopping. So we put minus T. Then the other process that can happen is when 2 bosons sit at a site, it costs some energy U. I'm trying to write a general Hamiltonian for bosons, right? So We don't have to have a hardcore constraint. It could be just some softer repulsion. Then we also may have some inter-site boson interaction. So there could be some other interactions, more general, say U prime and so on. And so if I want to describe this, the most general Hamiltonian you would write is, okay, minus T ij bi dagger bj plus the Hermitian conjugate, the reverse process. And then you could have some uij, ninj, and uij can have on-site, nearest neighbor, etc., etc. Hopping also could be between two neighboring sites or more distant, right? You could have all of that. I could even put T inside and make a Tij. But then you can also have a chemical potential which couples, so these are all operators, which couples to the density. And this chemical potential will control how many bosons you have. So the chemical potential directly controls that. Okay. Now you can construct a phase diagram in the parameter space of T, all of these U's and mu. In this space, you can construct a phase diagram. Is that clear?
Yes.
Okay. So that's kind of the most general problem. Now what we are seeing, so it depends how you map. If you start with spin problems, they come already with a lattice, and that lattice has a spin at every site, right? So that is usually telling you that you have either half-filled bosons or some definite density of local moments. So if you come from spins, it automatically dictates what density of bosons you have. On the other hand, if you come from bosons, you can generate any number in your system. Is that good?
Mm-hmm.
Okay, so let me see. So you got this. So let's see. Now we are going to run up against some time here. Let me do the following. Let me highlight a few key things that you guys can look at, and then we will discuss that next time. And I want to show you a few slides to make this a little more relevant. What do you think? Should I do that rather than stepping through the antiferromagnetic problem, or would you just like me to step through it?
Maybe we can read through the antiferromagnetic on our own and then discuss it next time.
Okay. So the key things to point out, and while you're reading, pay attention to these few things. So just like we talked about triplets in the ferromagnetic case, now, which screen am I sharing? This one. Now we will talk about, in the antiferromagnetic case, we will talk about singlets. And you will see that ultimately, let me show you a few really key results that come out in 1D, which is really very, very interesting. So I'm skipping ahead. And this is where I discuss a little bit of the Néel state represented in terms of bosons. And then I show how you can, how the XY term creates fluctuations in that. And what that does is that your ground state is no longer the Néel state, but it is a linear superposition of such singlet states, up, down, plus down, up. In the bosonic case, there has been a sign change, which you should try to understand carefully. This is where the discussion about the boson wave function not having a node comes in. Okay, so there's some tricky part there. And then let's come back and we will discuss this later. The key thing I want you to remember, or I want you to observe, is that when you include quantum fluctuations, the energy of the ground, of the Néel state, right, compared to the Néel state, the energy is lowered. That's why the system wants to include these quantum fluctuations. but the long range order is reduced. Okay, so let me just point that out here. So the nail state energy in 1D per site is minus a quarter J. When you include the quantum fluctuations, that energy is reduced to minus 0.42 J. So that's why your true ground state has a lot of these quantum fluctuations included in that. And the way to think about it in the boson language is that nail state basically means there's a pattern up, boson, empty, like that. By allowing the bosons to hop, you are, it is gaining kinetic energy, right? Compared to the localized state. And that's why this energy is becoming more negative. But now think of the long range order. Up, down, or a boson, empty is the perfect ordered state for an antiferromagnet. That's when the sublattice magnetization is half. By sublattice, I mean if you look on just the odd sites or the even sites, it's half. But if you look at quantum fluctuating ground state and ask what is the expectation value of SZ on the A sublattice, then you see that in 1D, this is an exact result, gives you 0. So that is what quantum fluctuations are doing. Okay, so this state would be called a spin liquid in 1D because it is not able to order because of these strong quantum fluctuations. In 2D, there aren't any exact results. There's Monte Carlo results. And this was actually my postdoctoral work back when. But in 2D, the nail state energy is minus half J. Quantum fluctuations reduce that energy to minus 0.7 J. But the long range order is not completely destroyed. You can see it's reduced from 0.5 to 0.36 on a square lattice, but it is not completely destroyed. Okay, that's, you should try to go through, at least understand what is involved in this. Now I want to connect what these, the order parameters look like in the boson sector. Okay, that brings in this very important concept of off-diagonal long-range order. Are people getting tired? Do you want a break? Let's stop for about 3 minutes. And then I'll go for the next 10, 15 minutes toward the end. But okay, so let me just say, we have kind of understood these mappings of Hamiltonians, states, energies, order parameters. What I want to do next is introduce the concept of what I call not what I call, but what is called the off-diagonal long-range order, which is a way of measuring the order parameter in the bosonic system. Yeah, let's take a little breather.
Yeah, so I had a question.
Sure.
Yeah, so these singlet pairs are only between the nearest neighbor sites, or they can be any site?
No, they can be they can be long range. They can involve even, yeah, they can be any length.
Okay.
It's a bit like, you know, when you do a quantum problem with a potential which is very, let's say you have an attractive potential, right? Which is a very short range potential. or a repulsive potential, let's say. The wave function is not just affected on that scale, it's affected on much longer scales, right? Because that has to do with the strength of the potential, not just the range.
Yeah.
So similarly here, the singlet pairs in the Hamiltonian, you may have just nearest neighbor interactions, but in the wave function, you can have much longer range singlets.
Can I ask a question as well?
Sure.
So, for example, going back to just like the classical Ising model, when I wanted to write down the ground state, I didn't really do anything mathematical. I just let my intuition guide me and say, oh, obviously, based off the Hamiltonian, it needs to be all up or all down or something. And so when we're getting to these more complicated Hamiltonians, and where not only do we have to think about the Hamiltonian, but also like the anti-commutation and the commutation relations of the operators, what is like the right process to go through to figure out the exact ground state? Like, for example, just looking at this bosonic Hamiltonian and knowing that there's also like the hardcore boson like commutation restraint, like I'm not really sure how I should start about writing down like an exact ground state wave function or something.
There are two things that define your problem, the Hamiltonian and the commutation relations, right?
Mm-hmm.
We don't always pay attention to that, but we have to know what kind of operators are these. So these two define the problem. Thereafter, what you're looking for is H psi equals E psi. You're just trying to find the eigenspectrum. And that's the way. So either you can, so when you say, okay, I'm going to try up, down, that's your approach is a variational approach. You're trying to see, is this the ground state, right? And so you can always find the energy in that state, but then you have to make sure that your Hamiltonian acting on that state gives you an eigenvalue E psi, gives you that state back. That's what you're looking for. So clearly, when you start with a boson empty, and you apply the Hamiltonian, that Hamiltonian generates more configurations where bosons have hopped from one side to another. So you don't get back that original state. So it can't be the ground state. So that means your ground state has these other configurations mixed in it, so that when the Hamiltonian acts on that linear superposition of states, you get back that state in that, right? If your eigenstate or your ground state is a linear superposition of many configurations, then when the Hamiltonian acts on that linear superposed set of states, you get back you get back that same state. Does that make sense?
So after, like, say I've found a state where it is an actual eigenstate of the Hamiltonian, how do I check that it also satisfies the commutation relation? Like, I guess I'm not even sure what that means exactly for a state to satisfy the hardcore.
I think the best thing is you should just try to work out, like, 2 sites I have done here. Just take 4 sites and try to construct, write all the, it's exactly how we do in classical problems as well. We write all the configurations and so on. Now here also you can write all the configurations, write out your Hamiltonian, and just try to exactly diagonalize that Hamiltonian. Okay, that will start giving you some picture of how to do a many body problem.
Okay.
You are not going to use a site basis. You will use a many particle basis, because these are many particle states. The Hilbert space is made up of these many particle states. So you will basically write down all the possible bosonic configurations, right? So each site can be either occupied or unoccupied. So you have 2 to the n configurations, and you write it all out, and then you perform the exact diagonalization. I think that will give you some idea about how the ground state is mixing configurations, and it's not one configuration describing the ground state.
Okay.
Okay, so any other questions?
So I have a quick question.
Yes.
So if a ground state is a massive superposition of different states, then can you do any numerical things to calculate the ground state energy?
Yeah, that's another very good question, Yanjun. So it comes back to those variational states that I brought up, right? That I said you can write down for different problems. So let's say for the hardcore problem, right? The one we are talking about right now.
Mm-hmm.
So your question, okay, is again, how can you calculate, right?
Mm-hmm.
Yeah. So it turns out that calculation is actually a very hard calculation, because think about it in this way. I have bosons with a hardcore constraint, right? How do you evaluate? Now for the energy, you need to evaluate the action of the Hamiltonian on this, and then the Hamiltonian will mix up everything, and then how do you handle 2 to the n configurations?
Mm-hmm.
So in fact, the way to do that is what is called variational Monte Carlo. And maybe this is something it's quite, so can you see me writing here?
Yes, yes.
Okay, okay. So here's kind of so the question that Yanjun is asking is, I have 2 to the n configurations, right? How do you calculate such a large set of expectation values? So one way, and this is not the only way, but one very powerful way is to use Monte Carlo methods, but kind of applied in quite a distinct way from classical Monte Carlo. So if you remember, let's just revisit classical Monte Carlo for Ising spins, right? So we had a problem, we had to do Z, sum over all the configurations of sigma, e to the minus beta, let's say energy evaluated for that configuration sigma I, right? And this is a sum of, and then you can put in any operator you want, and basically expectation value of any operator became sum over sigma I, operator value in that set of sigmas, and then weighted by this factor, e to the minus beta, e. Can you guys see my writing?
Yes.
Yeah.
Yes.
Is it even readable because I'm writing really fast?
It's good.
Okay. So the way we do this is so this is a huge number of configurations, 2 to the n configurations. Exactly solving the problem would be weighting it generating all the 2 to the n. But this is done using, let's say, Monte Carlo, by approximating this as sum over some finite set of configurations, some m configurations. And what you do is these m configurations are not random configurations, but what you do is you generate them weighted by this factor. So this is your probability, P of sigma. Okay, so that P times the O. O in that same sigma. I'm not repeating it. So what I'm saying is that this P is not now part of the sum. The M configurations are generated with probability P. Okay? How you do that, that's part of what is called, there are some procedures, Metropolis and so on, which I don't go into now. But what the main point is that you have reduced this sum over all configurations to a sum over just M configurations. M can be a very small number, and that number just tells you what your error bars are. So the smaller the error bars you want, the more M configurations you keep. But then you just evaluate your operator in those, let's say, 1,000, 10,000 configurations. Now, let's come to the quantum problem. The quantum problem, so quantum Monte Carlo. So this is, quantum Monte Carlo is like a word that identifies many different kinds of Monte Carlo. This particular one I'm talking about right now is what I would call a variational Monte Carlo, okay? And by that I mean you have proposed some wave function. So let's say some kind of this singlet wave function you have proposed. So that's your psi, which depends on R. So your configurations now are these so psi of R is some variational wave function, and R is a given set of configurations of these spins or bosons or whatever it is. So now our analogous problem is we want to evaluate the operator O as, let's say, sum over, so this is an expectation value. So this is psi, this is the many body wave function. Psi operator psi, normalized. Right now I can insert a complete set of states here and write it as psi R. Here they are all real for bosons, but suppose it was not, then mod psi square O of R. Let's assume it's a diagonal operator, which it need not be. There are more complications there. Mod square in the denominator, sum over R. This term is now exactly my P of R. So what I'm reducing the problem to is sum over R chosen from, instead this was all R. And this is chosen from a probability P of R. And now I evaluate O of R. Okay, so like if it's a density-density correlation, that's a diagonal operator. You can evaluate what its value will be for a few, like 1,000, 2,000, or configurations. But these configurations are not random. They are chosen from this probability. That's how it's done. So again, using Monte Carlo methods, Monte Carlo is a powerful method of sampling any probability distribution. In classical Monte Carlo, it's the thermally dictated distributions. Here, in variational Monte Carlo, it's configurations dictated by a wave function. And actually coming to the path integrals also, it's a very similar thing. So if you now have boson paths, what you're doing is this is X and this is tau, right? And what you get are these bosons which will hop around and generate one path. Another boson will also hop around and it'll have its path, and so on. And basically you want to evaluate operators as you sum over, kind of weighted by these different paths. So again, at every time step, you are generating so many configurations. Imagine. It would be an impossible task to do that by just enumerating. There are already 2 to the n configurations at tau equal to 0. Every time step, you generate another 2 to the n configurations. It's horrendously complicated. But again, Monte Carlo methods, extremely powerful, allow you to do that. And the Bose statistics and all of that also comes into that. And now the question is, what does it allow you to calculate? So let me show you one thing, and then we can discuss more next time. So this is one thing you would like to get at, and that's the ordering in the system. Okay, so when you have antiferromagnetic ordering, your spin-spin correlations on neighboring sites is just oscillating up, down, like that. So let me just get rid of that trivial oscillation. And then just by multiplying the spins on all the B sites by -1, and then you will see that your spin-spin correlations decay to some, and then decay exponentially, but then approach some constant if you have long-range order, right? We have discussed this. And that would indicate some magnetization in the Z direction. Similarly, if you look at S plus, S minus on 2 different sites, that would indicate at long distances, if it goes to a constant, that would tell you that you have ordering in the XY direction. So in a singlet, for example, which develops long-range order like this in an antiferromagnet, you will get equal ordering in the Z, X, and Y directions. Now, let's view it in the boson language. The long-range order of a bosonic system will really be reflected in this part. Okay, so what you are doing now, okay, this is a very important thing to understand. What you're doing is you're taking a certain state here. Let's say this is the ground state. And you are destroying a boson at some site J. You destroy, so you have some configuration. You can always expand size 0 in configurations, and you basically take your bosons, there's some site J here, and you are destroying this boson and tunneling it to another place, I, and you're creating a boson there, right? So you're hopping a boson from one site to another. And you're asking, can I return to the same state? So AI dagger, and can I return to my original wave function coherently? And if the system goes to a constant at large distances, it means you can return with some amplitude coherently. And that value that you return to is the condensate fraction. So if you Fourier transform this, it will show up in S of k, for example, as a delta function at k equal to 0. So that is the signature of a Bose condensate, that you have a macroscopic number of particles in the ground state. And that shows up as a delta function at k equal to 0. Okay, so if you have a BEC which is non-interacting, N0 is equal to N for a non-interacting BEC. If you have repulsive interactions which deplete the condensate, meaning all the particles can't remain at k equal to 0, they get depleted. By interactions, they get excited into higher momentum states. So you get something like this. Higher momentum states are occupied. This peak is not N0, but is depleted. It becomes less than that. This peak is going down to something here. So N0 is less than N in an interacting BEC. But it is still a BEC. It still has long range order so long as N0 is non-zero. If in a similar way in the magnetic case, it still has some XY order if you continue to have some N0. Okay, But if N0 goes to 0, then you have no long-range magnetic order in the XY direction. Okay, let's stop here. There are so many things to tell you guys about from here, but you'll see I had kept, there are such fantastic slides I was going to show you, but we will do all that next time. People have been able to, up until like say 2 decades back, the only example we really had was helium-4. And there was nothing you could tune. But what I want to tell you next time are these optical lattice experiments where you can take a trap, a magneto-optic trap, put bosons in it like rubidium and so on. These are neutral bosons. They have total spin 0 or total spin 1. That's how you make a bosonic atom. And they can turn on an optical lattice, meaning a lattice potential with some periodicity. And in this, they can change the wavelength of the lattice so they can make the minima further apart, which reduces the tunneling of the bosons from one side to another, so they can control hopping T. They can also constrain the lattice, the optical lattice, and make it very tight, so they can control U, which is the interaction between bosons, and they can control the number of bosons, mu. So now you have a totally tunable Hamiltonian. And in this, they can start to see phases and phase transitions. So I want to show you that next time. And what they measure is directly this N0, the condensate fraction. So there are 2 quantities we will focus on next time, N0 and superfluid stiffness. And I will, with that, come back to the XY model. Remember, the 2D XY model we did had a finite superfluid stiffness, but 0 condensate fraction. So we will discuss all of these next time. All I'm saying is spend the weekend at least reviewing some of these things, because now it's getting really hot, or I should say actually super cold, because we are going into ultra cold atoms. And we will see these phase transitions, and everything will come together. The XY model we did, I will connect that to a 1 + 1D mapped problem, and then we'll discuss ρs and N0. Okay.
Are we also going to have presentations on Friday?
Yes, we also have that. And I know some people were trying to reach me. I couldn't respond. I will now do that after today. Okay, great. See you all, and please make your masks, as I said, and wear your masks when you go out. It was super easy to make it. Even I could do it. It took me an hour, but I could do it. So the CDC website has many ideas. This was one of them with hairbands. You guys may not have hairbands, but you'll find shoelaces. So yeah. Okay. See you then. Bye.
Bye. Stay safe.
Bye.
Hi, Nandini.
Hi.
Do you have time to ask some questions?
Absolutely.
Could you explain the terminology, that why it is called off diagonal? Is that just because the AI and INJ are different?
No, it's because of the wording. They use ZZ correlations to mean diagonal. The terminology is that when you write a Hamiltonian in the Z basis.
Sorry, do you mean in the SD?
Yeah, let's come to the spin analog. So when you come to the SZ basis,
yeah,
right, that on the Hamiltonian, that gives you terms which are diagonal.
Okay.
And
yeah.
And so you can even think of our transverse fieldizing model, right? You had terms which were coupling to the SZ operators, and they gave you matrix. They gave you elements of the Hamiltonian which were on the diagonal, and then the SX parts gave you elements which were off diagonal.
Okay.
So
So do you mean it's because this is S plus S minus? So
yeah,
we call that.
yeah, that's right. So this is historical. Onsager and Penrose first used this word because of this analogy between AI dagger AJ being analogous to SX SX and SY SY correlators, which were off diagonal compared to the spin Z correlators.
Okay. Yeah, thank you. I have another question.
Yes.
It's about a point you mentioned several days ago that the quantum critical region. For example, we have, in 3D easy model. Yeah. Yes. Sorry. I just mean the phase diagram when at zero temperature there is a transition point from magnetic phase to paramagnetic phase to ferromagnetic phase, and we call that quantum phase transition point. And at finite temperature, there is still a classical phase transition line, right?
Yeah.
For example, the x-axis is a parameter and the y-axis is temperature. So you call a region where T is much larger than the gap, you call that quantum critical region. You say it's because it's controlled by the critical exponents are controlled by the quantum critical point. But is that true that all the points near the quantum critical region, not only the T much larger, but also T much smaller than gap, just so long as the point is in a small circle near the quantum critical region, it is controlled by the quantum critical point. Is that true?
Yeah, there is a circle, but let me see. Can you see my screen here?
Yeah.
Okay, let me try to just insert. So here is temperature, here is G.
Yeah.
So let's say this is the ordered phase.
Yeah.
It has some order parameter. So this is TC. And this is the disordered phase. So there is just some energy scale delta.
Yeah.
And this is disordered paramagnet. Okay, so around here, you're right, there is, so your point, like if I am, so your question is, okay, here you understand on this line,
yeah,
you understand that the correlations will be dictated by this.
Yeah, exactly.
Now your question is, what about here? Is that your question?
Yeah, you can also draw a circle around the critical point. Just,
like that.
Yeah, just any point near the circle, even the classical phase transition line has a,
That is correct. Even this classical. So what I'm trying to say is on this, like deep down here, it is going to be described by classical fluctuations here.
Because it's not near to the quantum critical point.
Because it's not near. Once
so
you,
why? So why do we only call the region with large temperature the quantum critical region? Is that just the terminal?
This one.
That, yeah. Why there? Why not in the circle? Like we draw like a bigger circle, and in the region it's quantum critical. Yeah.
So you're saying, why not make like this
Yeah.
and even these fluctuations? Yeah. So first of all, you have to be near some. So the way I like to think about it is try to make this is the way I like to think about it. Make a cut at finite temperature. Okay. So like suppose I make this cut like here.
Yeah.
Versus I make a cut here. Okay.
What
So
does it mean?
I make two cuts. So here I'm at high temperature and I'm cutting this TC and I'm going to ask what kind of fluctuations. I start at this temperature.
Yeah.
You can see here. Okay. So I start at this temperature in the ordered phase.
Yeah.
And then I increase G and I come to the transition.
Yeah.
And I ask, what is T, how is the behavior scaling here?
Yeah.
Right?
Yeah.
Which critical point is dictating this behavior?
Yeah.
And that will be pretty much the classical exponents.
Exactly.
Okay,
I agree.
now you do this one.
Yeah.
Okay, what will happen in this cut is, you're at very low temperatures. So pretty much whatever thermal, suppose you're looking at susceptibility.
Yeah.
So you have some system and you're looking at magnetic susceptibility on different locations. You get some distribution of susceptibilities.
Yeah.
Now, it has some small width because the temperature is low, right? Now you keep the same temperature, but you increase G.
Yeah.
So now what will happen to your susceptibility?
I think there are two regions near the classical phase transition point. It's controlled by classical phase transition, and like at a point far away from classical phase transition point, it is controlled by quantum point.
Yeah, but what would that mean? If when you say controlled by, how will you see it in the data? Like suppose you have your susceptibility here with some distribution, right?
Yeah.
So I'm plotting P of chi versus chi, right? And it has some distribution, very small width because temperature is very low, right?
Yeah. So we are we measuring
yeah.
So we measure for example, one of the critical exponents, chi as a function of G, right? It was supposed to be a power law. And the power is, there are two powers, one of the classical and one of the quantum.
Exactly. Exactly. So you will see it change its power law behavior. You will see a better fit with the power law of behavior dictated by this G.
Yeah, so there is a crossover from.
There's a crossover
from quantum power law to the classical power law.
Yes.
Yeah. So I think I agree with all the phenomena, but I still don't understand the term why only the region within the green cone is called quantum critical region.
Okay. The reason is, think of critical region. Critical region means there is no scale.
Yeah.
Okay, this is the single important idea, that if you have a scale in the problem, like if you have exponential decay, that means there is a scale in the problem.
Yeah.
If you have power laws, that means there is no scale.
Yeah, yeah.
So now the point is, let me say I'm coming along this line. I'm still below TC.
Yeah.
Now I have a scale in the problem.
Yeah, yeah.
Okay, when I go above TC, right? When I go above TC, I have now, so now there are two possibilities. So now I understand your question. You're saying, let me go above TC. How do I know I am just disordered versus I am in quantum critical? Is that your question? That here I am in a regime where there is no ordering, but I'm calling the region within the green lines critical, and the region outside the green lines just kind of some classical behavior. But here I'm calling it quantum behavior. Is that the question?
Yeah, I think so.
Yeah. Okay, that's the question, right?
Yeah.
So like when I make a circle, pretty much everything is quantum critical here because it's a more or less very close to the quantum critical point.
Yeah, exactly.
When I go further away, there is some fan. I think you're asking me, why do I have a fan?
Yeah, instead of a circle.
Instead of a circle, like everything outside the red line, why is that not quantum critical? Is that what you're asking?
Sorry, could you repeat the
You are saying, when I look above this red line, why is everything not quantum critical? Why is only the green, bounded by the green fan, why is only that quantum critical?
Which red line do you mean?
This one, are you able to see my?
Do you draw? Are you drawing?
Yeah. Let's see. Are you seeing here?
Yeah, I see that.
Okay, so
The
here,
green one.
Yeah, let me make it green. So this fan, I think you're asking, why is this quantum critical and not this?
I even want to call the order and disorder phase near the G point also quantum critical.
Yeah, the G point is also, so let me draw this little better. I think I see what your question is. Let me expand that.
I just want to call the region within the green circle.
Yeah.
Even including the classical phase transition point, because the scaling of classical phase transition temperature is also controlled by the scaling of quantum critical point.
So here is the picture. Okay, ordered, disordered. Now, what are you wanting to call quantum critical? Let me first understand.
In a circle around the quantum critical point.
So this circle.
Yeah, within that region.
Including this and this.
Yeah, it even includes the classical phase transition point.
So pretty much, okay, so now, okay, and are you, so this is very close to the quantum critical point, but are you trying to say even if I make a bigger circle like this?
It doesn't.
See, the reason I'm asking is I want to understand where your question is, because like if I make this fan, right?
But when you are making that fan, you also mean the region must be near to the quantum critical
I also
point.
mean it must be near. And pretty much when you make this circle, this one,
yeah,
it is more or less including everything. It's so difficult to distinguish that. But are you asking why the fan expands outward?
No. I think I don't care much about the expansion of the fan, but more about the angle. Why it's only a why not a circle, but a fan of a particular angle?
What determines this angle, you're saying?
Yeah. Where do we use that condition? It seems.
Okay, that is dictated by a particular exponent z. There's an exponent, dynamical exponent, which controls that angle.
Yeah, I know. The condition seems like temperature is much larger than G minus GC to the Z mu,
yeah,
something like that.
Yeah.
But Where do we use that definition?
Where is it coming from?
Um,
So
let me put it this way. So we call that quantum critical region because, like you said, some. I think the example you gave is the superconductivity. Like the temperature is it's hard to explain. Okay.